Here is a tiny program and one simple question. We set x to 0. Then, for I running from 1 to 4, we keep adding I onto x. When the loop finishes, what is x? Now you could guess, but a computer never guesses. It never says about 10. It executes every line, in order exactly, and lands on one precise number. So the skill for today is to become the machine. To take any algorithm and predict exactly what it does by tracking every variable, step by step. We call this a dry run, and the tool that makes it reliable is the trace table. That table is the bridge from writing code to reasoning about algorithms. So let's learn to read it. Pseudocode is just code with the fussy details stripped away. The plain shape of an algorithm. A left arrow means assignment. X gets the value 5, stored in the box named X. A line like X gets X plus 1 is an update. Read the old X, add 1, and write the result back into the same box. Same variable, new value. A capital letter with a square bracket is an array, a row of values. A bracket I means the element sitting at position I. In this lesson, our positions start counting at 1. For I from 1 to n is a counting loop. I takes the values 1, 2, and so on, up to and including n. The body runs once for each. And if tests a condition, is a at I bigger than its neighbor? A at I plus 1. If yes, we do one thing. If no, another. And mod is the remainder after division. I mod to equals 0 asks, is I even? These 6 pieces are the whole vocabulary. Now we make them move. A trace table is small and mechanical, and that is its power. You draw one column for every variable that changes. Here, that is I. The counter and X are running total. Then you add one row for every step the machine takes. Usually, one row per turn of the loop. Each cell records a variable's value right after that step. Fill the rows in order, and the final row is your answer. Let me show you the rhythm. See how X grows down the column 1, 3, 6. As the counter climbs, the state of the whole program laid out on paper. No juggling in your head. Let's fill one completely. Our first full dry run, running some of the numbers 1 to 4. Write the columns, I and sum, and record the starting value. Sum is 0 before the loop even begins. I is 1. Sum was 0 plus 1 is 1. First row, I is 2. Sum was 1 plus 2 gives 3. I is 3. 3 plus 3 is 6. I is 4, the last value. 6 plus 4 is 10. The loop ends here. Read the final row. Sum equals 10. Not about 10, exactly 10. And notice the counter stopped at 4, because 1 to 4 includes 4. That inclusive bound is the single most common thing people get wrong. So we will watch it closely. Same rhythm, but now we multiply instead of add. This loop computes 3 to the 4th power. Result starts at 1, base is 3, and each turn multiplies result by base. K is 1, result 1 times 3 is 3. K is 2 3 times. 3 is 9. K is 3. 9 times 3 is 27. K is 4. 27 times 3 is 81. Final result, 81, which is 3 times 3 times 3 times 3 times 3, exactly 3 to the 4th. Because we always overwrote result with result times base, the value compounds down the column. Starting from 1, not 0, was essential. A product that begins at 0 stays 0 forever. Before we reverse anything, the humble swap, trading to values. Say A holds 5 and B holds 9, and we want them exchanged. Here is the trap. If you just wrote a gets B, you would clobber the 5 before you ever saved it. It is gone. So we use a temporary box. Temp gets a 5 is now safely parked in temp. Now A gets B. A becomes 9. We overwrite A. But that is fine. The 5 is safe. And B gets temp. B becomes 5. The swap is done. A is 9. B is 5. A swap always needs that third box. Now reverse a whole array in place, using two pointers that walk toward each other. Low starts at the first position, high at the last. While low is still left of high, swap those two elements. Then step low, right and high left. First swap, low is 1, high is 5. Trade 10 and 50. The row becomes 50, 20, 30, 40, 10. Then low moves to 2, high to 4, closing in. Second swap. Trade 20 and 40. Now it reads 50, 40, 30, 20, 10. Low steps to 3, high steps to 3. And now low equals high. They have met in the middle. So low is no longer strictly less than high. And the loop stops. The array is fully reversed. 50, 40, 30, 20, 10. The pointers meeting is the signal to halt. Now the classic bubble sort traced all the way to sorted. We have four numbers: 5, 2, 4, 1. The idea: repeatedly compare each neighboring pair, and if they are out of order, swap them. Larger values bubble to the right. Our table logs the pass I, the position j, and the whole array after each step. Pass 1. Compare j1 5 versus 2. 5 is bigger, so swap. Array 2, 5, 4, 1. j2 5 versus 4. Swap. 2, 4, 5, 1. j3 5 versus 1. Swap. 2, 4, 1, 5. The 5 has bubbled all the way to the end. It is now in place. Pass 2 only needs to reach j2. j1 2 versus 4. 2 is smaller, in order, so no swap. j2 4 versus 1. Swap. 2, 1, 4, 5. Now 4 is settled too. Pass 3. Just j1. 2 versus 1. Swap. 1, 2, 4, 5. And we are sorted. Final array. 1, 2, 4, 5. Fully sorted, and we got there by tracing every single comparison. Notice pass 2 stopped early, and pass 3 earlier still, because each pass locks one more big value at the end. Watching the array reorder, box by box, is exactly how you understand any sorting algorithm. A loop inside a loop needs extra care, because the inner one can run a different number of times for each outer step. Here the inner bound is j from 1 to I. It depends on I. Count starts at 0. Outer I 1. Inner j runs only up to 1. A single pass. Count becomes 1. Outer I 2. Inner j goes 1 to 2. First inner pass. j1. Count is 2. Still I2 j2. Count is 3. Outer I3. Inner j goes 1 to 3. j1. Count 4. j2. Count 5. j3. Count 6. Final count 6. Because the inner loop ran 1, then 2, then 3 times. 1 plus 2 plus 3. If instead the inner bound had been a fixed 3, it would run 3 times every pass. 3 times 3, 9. The difference is whether that inner bound leans on the outer counter. Always write the pairs out. Your turn. A while loop this time. N starts at 4, S at 0. While N is greater than 0, add N to S, then knock N down by 1. Pause right now. Build the trace table yourself and predict the final S. Remember to track both variables. I'll wait. N is 4, greater than 0. S becomes 0 plus 4, 4. Then N drops to 3. N is 3, still positive. S becomes 4 plus 3, 7. N drops to 2. N is 2. S becomes 7 plus 2, 9. N drops to 1. N is 1. S becomes 9 plus 1, 10. N drops to 0. Now N is 0. The condition N greater than 0 is false. So the loop ends without running the body again. Final S is 10, which is 4 plus 3 plus 2 plus 1. If you traced n all the way down to 0 and got 10, you have got it. That last check, is the condition still true, is what tells a while loop when to stop. Trap 1, the classic, off by 1. For I from 1 to 4 runs at I equals 4 as well. The upper bound is included. Always write out the actual I values and check the first and the last iteration by hand. Trap 2, ignoring initial values. If a counter secretly starts at 5 and you assume 0, every row is off. Record every starting value before the loop. Trap 3, order matters. If you set x first, then set y from x, the y uses the new x. Apply the assignment strictly top to bottom, using current values. Trap 4, a swap without a temporary. Writing a gets B, then B gets A, destroys the original A before you can save it. You need the third box. And trap 5, track everything that changes, not only the headline variable, the loop counter, the temp, and array cell. A value you forget to follow is a value you will get wrong. Let's lock in the method. First, read the pseudocode slowly, line by line. Note every variable, its starting value, the loop bounds, and each if. Second, write out the loop ranges explicitly. For I from 1 to n means I is 1 to, all the way to n including n. Third, draw one column for each variable that changes, the counters, the accumulators, and any array cell that moves. Fourth, fill one row per step, applying every line in the order written, always with the current values. And fifth, read the final row for your answer. Then sanity check it. Do a dry run like this, and predicting what any algorithm does stops being a guess and becomes a reliable mechanical skill. That is the doorway into algorithms.